Okay, welcome everyone to this Nexus Project webinar. My name's Brendan Cullen and I am from the University of Melbourne, I've led the Nexus Project out of the University of Melbourne, and we've got a number of our presenters on the screen that you can see. So we're going to do a national look at Nexus Project and related projects, which have been looking at really the intersection of climate variability, climate change, and other pressures around reducing greenhouse gas emissions from livestock production systems. So the program for today will be, we'll take this tour around and I'll give you a bit more details about that, how we're going to do it. So we're covering Victoria, New South Wales, Queensland, Tasmania, and Western Australia. You can see our project partners along the bottom of the screen there. So Meat and Livestock Australia have funded this work, along with funding and resources from all the other organisations. So Tasmanian Institute of Agriculture, University of Southern Queensland, CSIRO, who are not on this today, but were part of the project, and Department of Primary Industries and Regional Development in Western Australia. Okay, let's get into it. So the Nexus Project, as I said, is really about exploring this nexus, as we put it, between the profitability, productivity, and greenhouse gas mitigation, or reducing greenhouse gas emissions in the context of an increasingly variable climate. So we've done case studies through University of Melbourne, through Victoria and New South Wales. Matthew Harrison and his team have done 2 case studies in Tasmania. Duc-Anh has done a case study in central Queensland, and Paul Sanford and Kevin Foster will also be talking about their work in Western Australia, which is not formally part of the Nexus Project, but it's part of the Future Sheep Project, which has some similar methodologies to what we've done in the Nexus Project. So we thought it'd be a great opportunity to bring everyone together and talk about the results and paint this broad picture of the work. Before we get started, I'd like to collect a little bit of information about who's in the audience today. So I'm going to just launch a poll. So we've got quite an even split of people from Victoria, Tasmania, and New South Wales, and Western Australia are strongly represented as well. A couple of internationals too. In terms of who's here, research and academia and government pretty well represented. Not a lot of farmers on the line, but I know a lot of people do register and then watch the recording later on. Quite an even split between beef and sheep production, and other as well in there. That might be some of the researchers that have answered in there. Livestock numbers, small producers, 0 to 100, and also some larger producers in there, greater than 1,000. So what's the reason? To hear the latest research, know some of the presenters, adapting to climate change, reducing greenhouse gas emissions. Yes, so a broad range of interests there, and hopefully we can cater to that. Okay, let's get into the background to the Nexus Project. So we know that the climate is changing. We know that temperatures are increasing. And we can see that from some of the data here, just at broad scale across the Australian continent. Temperatures have warmed by about 1.5 degrees since 1910, and this data comes from the State of the Climate report. In the Nexus Project, we are focused on looking at the future, so looking out to 2030, which is not far away, looking out to 2050, and what is expected to increase. So without going through all the details, the things that we can expect to see over that time period are continuing to increase in temperature. So I think about this as a lot as the trends that we're already seeing to continue. So increase in temperatures, more hot extremes, so more heat waves. Also increased number of dangerous fire days and a longer fire season, so a longer kind of summer period. So we have a lot of confidence from the climate science that the temperatures will continue to increase. We'll also see we've also seen changes in rainfall patterns. So in particular, what's striking across southern Australia has been the decline in the cool season rainfall. So this graph shows the April to October rainfall. It highlights the last 20-year period relative to the climate record that we have. So you can see many areas of southwestern, South Australia and southeastern Australia have been lowest on record or very much below average over that period. So this is the climate that we have experienced in the last 20 years. So we've seen that decline, and I guess probably the key future projection is that that decline in cool season rainfall is predicted to continue. We'll have more time in drought with that lower rainfall, but with short duration heavy rainfall events. So more of our rain being concentrated in fewer larger events. So when we're dealing with the future climates in this project, we try to build those extreme events into the climate projections that we use. The other pressure that we've dealt with is this need to reduce greenhouse gas emissions from agriculture. So that's coming from different sectors. It's coming from industry, so Meat and Livestock Australia with their target towards carbon neutral 2030. It's coming from the food supply chain as well. So a quote there as well from JBS, one of the big global food companies, about their ambition to reduce net emissions to zero by 2040. So this need to reduce emissions is coming at the industry as well. So we're looking at scenarios in this project to meet both those challenges about reducing emissions and also adapting to the changing climate. How do we do it? We work in a really multidisciplinary way in the Nexus project. So we use regional reference groups, so we involve farmer groups and consultants in the research methodology. So they help us to choose a case study farm. We always use we mostly use real farms in this work, so it's grounded in the reality that farm businesses face. So we're thinking about these future challenges in climate, greenhouse gas emissions, using the climate science to develop climate scenarios for 2030 and 2050. We're not just thinking about the farm as it is, but how it might adapt as well. So thinking about what technologies are out there that can change now, that can help these systems adapt, but also thinking about new technologies, so emerging technologies on the horizon that might be transformational in the way that we can adapt to climate change and reduce greenhouse gas emissions. We use biophysical and economic modelling approaches. So economics is a strong component of this. We also use social research methodologies, and we've got members from our social research team here speaking today as well. So to try and get an integrated assessment of the different options that we explore. And we continually loop back to our reference groups. So our reference groups are really important, not just to set the project up, but to road test the results and make sure it's relevant to the industry needs. The case studies that we've looked at in the Nexus project span all the way from the Midlands in Tasmania, looking at sheep flocks, through to North Queensland, Central and North Queensland, looking at beef herds. So the aim was to set up a series of case studies across Eastern Australia, representing the different climatic zones and different sorts of production systems. So we've had that series of 7 case studies that we've investigated. The Future Sheep project, which Paul and Kevin will talk about later, has looked at 3 different sites and case studies in southwestern Western Australia. Snapshot of some of our case studies from North Queensland in the kind of Mitchell grass plains through to the rolling hills of East Gippsland, cool temperate climates in northwestern Australia, and into the sheep zone and mixed cropping zone through southeastern part of Western Australia. Our regional reference groups, this just shows how we did interact with the farmers. So photos from some of our regional reference groups. So these were integral. So we usually had about six or so regional producers, case study farmers, consultants who came together, 5 or 6 times throughout the project to guide the project in setting up the questions, making sure the options that we investigate were relevant to their region. Each project used slightly different approaches, but broadly we had these different alternative farm scenarios that we looked at. So we could look at continuing to run the farm as it is and what that did to what climate change did to that. We could adapt. So this is adapt, or low-hanging fruit is a series of improvements that adapt farms to the changing climate. So best management practices, things that farmers are already thinking about and implementing on their farm. So see how that can help us adapt to the climate. Towards carbon neutral was a focus on reducing emissions from the farm system. So what combination of technologies could we put together to reduce, to focus on reducing greenhouse gas emissions from the farm? Diversify and grow was another pathway. So this is increasing scale of the farm operation, getting bigger, sometimes looking at spatial diversification of the farm, using different regions with different climatic patterns to reduce the climate risk. And we also looked at some of the transformational options. So new technologies like methane inhibitors or new pasture species, which might be able to help us adapt and reduce emissions more into the future. So that was the broad framework of the project. So I want to just give a snapshot of results from the work that we did at Melbourne Uni. So I'm just going, we did 3 case studies. We did the East Gippsland, Northern Victoria, and one in the Upper Hunter region of New South Wales. I'm just going to mainly focus on Northern Victoria to give a snapshot of results. Our project team is listed there. I won't go through everyone, but it's farm systems modelers, it's social researchers, it's farm economists, all working together, animal scientists as well, to analyse these case studies. Climate impacts a lot on the farm systems through changes in pasture growth patterns. So the 6 different climate scenarios that we looked at are listed on the right-hand side of the screen. We looked at historical, which is 1986 to 2005, recent, which is our last 20-year period, and then 2030 and 2050. So 2030, we looked at a mid-level change, and 2030, we looked at a hot and dry extreme. So some of the trends that we've seen are more at the extreme end of temperature change and drying. So that's why we looked at that extreme as well. So we can see in East Gippsland here with a Phalaris subclover lucerne mixed pasture system, we see a bit of a boost in growth through the winter and early spring period, but generally a contraction of that spring growing season and summer growing season. So particularly under the hot and dry climate scenarios. So that's pretty typical of what we see in the climate scenarios. In Northern Victoria, in Phalaris and subclover systems, similar types of patterns. So a boost in winter production, and farmers recognised as well that that they have seen that winter limitation being overcome through the changing climate and changing pasture species. But again, this contraction of the spring growing season. New South Wales have chosen to illustrate this on the right-hand side there with a tropical grass. So this is one of the adaptations that we looked at in New South Wales. Tropical grass using the summer rainfall. The case study farm there had been mainly temperates, but transitioning into more tropical pastures, which are more persistent and more productive. So the tropical grass pastures don't have as much impact in the future climate scenarios as what the temperate species does. So that had adaptation potential in that region. Adapting the farm, some of the key components were improving the feed base. So in Gippsland, that was about summer active mixtures that could use the rainfall when it grows. In Northern Victoria, it was about maximising production in that relatively short but reliable part of the growing season. So strategic use of nitrogen fertiliser, gibberellic acid to grow as much as you can in that reliable part of the season before the season contracts. New South Wales was about tropical species. Improving livestock production, so lamb survival, genetics to increase lambing rates, for example, by about 15%, increase livestock growth rates through genetic improvement, changes to management like earlier lambing and selling times, and also planting trees in unproductive areas of the farm for shelter, but also for carbon sequestration. Towards carbon neutral, now we looked at implementing some of the emissions reductions through feeding supplements, but it was pretty limited in what we could do in these pasture-based systems. So it was a bit about confinement feeding, a bit about feeding strategically for earlier finishing, and including feed additives like 3-NOP to reduce emissions for those groups of animals. But it wasn't, broad scale to all animals on the farm because there weren't, enough. It wasn't practical. So forestry or environmental plantings, tree plantings on up to about 20% of the farm area did most of the work in reducing the emissions, so carbon sequestration. Our diversify and grow options really was increasing the scale of livestock production. So in our Northern Victoria case study, which was based up around Violet Town, that involved buying a farm in southwest Victoria and increasing scale and diversifying the climate risk. So they're the options. And they were broadly similar across our three different case studies. So let's look at greenhouse gas emissions. So our base farm had about 3,500 tonnes of carbon greenhouse gas emissions, so carbon dioxide equivalents. Methane emissions intensity, so 7.6 for sheep meat production, 27 for wool, and 10 for beef. So this is a pretty efficient when you compare this with other data, particularly for the beef enterprise, really at the low end of what we might expect. If we adapt, so we've got more animals and a bit of extra fertiliser use here, we've increased emissions slightly from the farm, but we've reduced the emissions intensity because we're turning off more animals. So we're becoming more efficient. If we grow and diversify, we're expanding the livestock business. So we've expanded, so the greenhouse gas emissions have increased as a result of that. And carbon neutral, we actually drove this farm down to carbon neutral largely through tree planting. So we're actually sequestering a little bit of carbon in the farm there. But it was offsetting or sequestering carbon rather than reducing emissions. So we bought additional land and used that as forestry was the main mechanism that we achieved that. So what's the impact on farm profit? So this shows the return. So we buy the farm, we run it for 20 years and we sell it. That's how we did the economic analysis. So here, the zero line here, we're earning 7% return on capital, which is equivalent to other investments. So if we're in the historical climate, we've added value to the farm. Really the shape of the relative position of these box and whiskers is important. So in the historical climate, we're up here. In our 2030 climate scenarios, profit has fallen or the value has fallen. And in our 2050 climate scenarios, particularly in that 2050 hot and dry scenario, our economic improvement, our economic position has fallen. So the future climate's reduced pasture growth is adding additional costs to the farm. If we look at our other scenario, so our adapt scenario, our grow scenario, and our carbon neutral scenario, we can see by adapting, doing those things I mentioned before, we've shifted up the economic performance of the farm a little bit. Diversifying, growing the farm business has increased profitability of these farms as well. But you can see the bars are wider. So there's more economic and financial risk associated with them. Towards carbon neutral was interesting, and you can see it's the lowest here. So there were additional costs associated with that carbon neutral production system. So by having trees on the farms, we're either giving up pasture, or agroforestry systems are not as profitable as livestock. So the financial return there is lower. So we haven't sold any carbon credits, we haven't purchased any carbon, or haven't had to pay a carbon tax here, but there is, our research showed there was a cost to those farm systems. Some of the new technologies we looked at, if we can have a methane inhibitor as a slow release bolus, achieving similar to what can be achieved in feedlots now, improving animal efficiency, so feed conversion efficiency through reduced mature size, and some are active pasture species or higher quality pasture species. In Northern Victoria, we looked at summer active species. So a methane inhibitor would greatly reduce methane emissions, and I guess we're putting a lot of hope in that technology coming down the line. Animal genetics, so feed conversion efficiency and reduced mature size, that can also help to reduce our methane emissions relative to our adapted farm up the top there. And if we can combine new pastures with animal efficiency and methane inhibitors, then we can make a really big dent in the emissions profile. One thing to note, just in terms of the profitability in our 2050 hot and dry scenarios, in our really extreme scenarios, it really was this change to the feed base, this summer active pasture mix, which showed the most potential to increase profit in those more extreme climate scenarios. So the feed base is really important in terms of we keep trying to improve the feed base in the context of changing climate. So there were some regional differences between our three case study farms. Northern New South Wales might be less impacted than the Victorian case studies because there's less of a rainfall reduction and more feed-based options. The adapt option can overcome some of the negative impacts of climate change, but not so much though at the extremes of that hot and dry. The grow option looks profitable, but does have additional risk. Towards carbon neutral does add costs to the business with the current technology that we've got now, and new technologies will play a key role in that. So that's a quick snapshot of the modelling. I want to hand over now to Nicole Reichelt to just talk about the social research from these case studies.
Thanks, Brendan. I'll just grab my presentation slides and make sure it's in presenter mode. Okay, I take it that everybody can see that now?
Yep, that's good.
Okay, terrific. So yes, my name is Nicole Reichelt, and I am part of the University of Melbourne social research team, which also includes Margaret Eyre and Ruth Nettle, whom some of you may know. The main purpose for the social research was to add to the climate and farm system modelling by identifying what human and social capacities may be needed to implement the modelled Nexus pathways. This included what opportunities and challenges there might be in putting the adapt, diversifying, grow, and towards carbon neutral pathways into action. So by understanding the current capacity to implement the modelled Nexus pathways of the reference group members, this would help lead us to scoping ways in which to support and strengthen the adaptive capacity of the red meat producers in the Nexus case study regions. So we used two main methods to answer our research questions. The first method was facilitating a series of focus group discussions with the reference groups over the course of the project, where we held over 15 reference group meetings across our three case studies. So during those meetings, we posed questions to the reference group members to gain insights into what the reference group members were thinking about the Nexus adaptation pathways and what RD&E might be needed to enable these pathways to be actioned. To complement the focus group discussions, we also asked reference group members to complete a questionnaire that required them to self-assess their own adaptive capacity if they were a producer, or assess their client base if they were a livestock advisor, based on rating a series of statements to indicate how able they currently are to implement the Nexus pathways in relation to access and use of a range of resources covering human, social, physical, financial and natural resources. So the next slide provides the key findings from the focus groups and questionnaire. So in terms of the focus group discussions, the overall sentiment for each of the Nexus pathways was as follows. So for the ADAPT pathway, mostly this was considered a very doable pathway, and it is a reflection of what reference group members were currently doing. And it was considered to be, should be normal practice in the red meat industry. You know, in the words of one reference group member, cute and shiny options are more of a distraction to good livestock production principles, such as efficient use of inputs to maintain or increase outputs over time and applying best practices to livestock and pasture management. So ADAPT should be just the normal practice of livestock producers in this day and age. With diversifying and growing the farm business, this was considered desirable, but the challenges to this pathway were increased land values, sometimes making it unaffordable to purchase additional land. You also needed to invest in additional infrastructure, perhaps develop new skills for managing woodlots if you're using additional land for woodlot management, for carbon credits and ecological services. You also needed capacity to access and manage and integrate additional labour units to work the additional land or new business activity. In terms of transitioning towards carbon neutral, this was considered an inevitable change challenge, regardless of whether it was viewed as an obligatory change, a business cost, or an opportunity. So while there was great interest in mitigating greenhouse gas emissions in red meat production, there was also significant confusion about how to account for carbon and greenhouse gas emissions in red meat production, and significant resistance and scepticism about what benefits could be generated from accumulating carbon credits and sequestering carbon in biomass. So basically, the return on investment of carbon neutral agriculture is still unclear. For the transformational pathway, there is a general interest in adopting new technologies. However, producers are still learning about what technologies are market ready and how these technologies can be consistently used to add value to their farm business. Heading on to the results of the questionnaire, in terms of indicating the adaptive capacity of the reference groups to implement the Nexus pathways, across all three reference groups, there was generally more capacity to implement the adapt and diversify and grow pathways, which are the blue and green lines in the radar charts, and less capacity to implement the towards carbon neutral pathway, which are the orange lines in the radar charts. So these three radar charts represent the average rating of each capital type by the reference group members in terms of how available and if they're using human, social, physical, financial and natural resources for each Nexus pathway. So anything beyond the black dotted line indicates more capacity, more access to use of resources for adaptation and mitigation, and anything within the black dotted lines indicates less access and use of resources for adaptation and mitigation. So in terms of having access and to use to particular resources, the East Gippsland and Northern New South Wales reference groups indicated that they have more capacity to implement all three Nexus pathways, including the towards carbon neutral pathway, when it comes to drawing on human and natural capitals. And what I mean by human and natural capitals, I'm talking about skills, confidence, practical know-how, accessing good soils and livestock breeds and climate. However, across all reference groups, there was a tendency to indicate that there is currently less capacity to implement all three Nexus pathways when it comes to drawing on social, physical and financial resources. So by social capital, I'm referring to government and industry settings. I'm talking about current offerings of agricultural farm services, and I'm also talking about the unavailability of peer networks that focus on innovative adaptation mitigation options. By physical capital, I mean adaptation and mitigation is considered constrained by current lending conditions of financial institutions, farm income and lack of financial risk analyses for adaptation and mitigation. By financial capital, I'm referring to adaptation and mitigation being considered constrained by current farm water storage, regional water infrastructure and information communications technology infrastructure. So what does all this mean at the end of the day? So it highlights the importance of investing and building the physical, financial and social capitals of livestock production regions for climate change adaptation mitigation, rather than framing adaptation mitigation as a practice largely reliant on human skills alone. The findings infer that we shouldn't assume that if a producer can implement one adaptation pathway, then they can automatically implement another adaptation pathway. Therefore, it's important to provide extension and advisory services that are designed to support specific adaptation and mitigation activities, rather than basing services around a broad understanding of red meat production regions' general capacity for adaptation. Also, alongside the strengthening of social, financial and physical capitals in a production region, support for adaptation mitigation of red meat producers may be best designed as flexible packages of various adaptation mitigation options, rather than framing adaptation and mitigation as discrete pathways, because producers may want to implement certain elements of all three pathways simultaneously, or assemble and reassemble adaptation mitigation activities over time, depending on changing personal goals and external operating conditions, or they might want to stagger the timing of adaptation and mitigation activities as part of a strategic plan. So this is based on reference groups indicating their individual preferences for the Nexus pathways and their different capabilities to implement them. And just finally, in terms of what reference groups thought of their experiences with the Nexus project, it was definitely an opportunity to think strategically about adaptation and mitigation, and to explore what a future red meat production system might look like out to 2050. The project also validated the adaptation practices that are already happening on ground. So that was a great comfort to a lot of the producers and advisors in the room. Just based on feedback from reference groups, if we were to conduct another Nexus-like project, there are just a couple of things that could be focused on more so than we did in our current research Nexus project. So there were suggestions that there needs to be a greater focus on taking out the risks and uncertainties with implementing a towards carbon neutral pathway. And one way to do this would be selecting a few producers to take a towards carbon neutral pathway and follow and support their journey over a couple of years to watch the implementation happening in real time. And also there might need to be a greater focus on adaptation and mitigation efforts and to add value for the business, environment and people. So looking at more of the triple bottom line as an integrated response to climate change. Thank you. I'll just stop sharing now.
Thanks, Nikki. That was great. We're going to move straight on now and move to Tasmania. So I'll introduce Matthew Harrison to you to take us through the Tasmanian results.
Thanks, Brendan. I'll see if I can share my screen without any dramas. Can you see that now?
Yep, got it, Matt. Perfect.
Yep. So I was the leader of the Nexus project in Tasmania, but there was quite a large team involved. There was also an associated or sister project, the Legumes Project, which was led by Rowan Smith, and I think that's still going. So we had 2 case study farms, and Brendan briefly touched on those at the start. One of those, if you see that little inset map of Tasmania in the corner there, one of them was near Campbelltown, which is the Tasmanian Midlands, and that's about 580 millimetres a year. The Legumes Project actually had pasture genotype trials on that farm. So that was a good way to test some of the genotypes on that farm and get growers along to the case study farm. One of those genotypes was Tallish clover, which we modelled as a pasture renovation to the feed base. The other farm was in the northwest, near Stanley, near the nut, and very different production systems, about 940 millimetres a year. It's a deep red ferrosol, so very different soil types, a much more sort of productive system. That was a beef cattle enterprise, whereas the one in the Midlands was a sheep enterprise. So very different enterprises and production systems. The main result that we found of the impacts of climate change, and we used the same climate methodology as Brendan just presented, was a slightly modest or even slightly beneficial impact of changing climate in Tasmania. Temperatures did go up and rainfall did go down. So we had about 11% increase in mean temperature by 2050. And that was mostly in late autumn and early spring. Rainfall did go down, although there wasn't really any seasonal trends. It went down in winter, and that was a benefit in the northwest because pasture growth tended to be constrained by temperature rather than rainfall. Spring growing season, similar to those charts that Brendan showed, contracted over the 30-year climate duration, although some seasons was more beneficial. What we found is lamb mortality for the sheep farm went down. That was because we had slightly milder winters and slightly warmer springs. So that's really a productivity co-benefit. So we had slightly less mortality and slightly greater productivity. So overall, modest and even slightly beneficial impacts of climate change, but we did see that you'd need greater agility in your management to cope with these extremes. We did show that soil carbon went down, soil carbon sequestration. So by 2050, I think it went down by between 45 to 133%. Now that's soil carbon sequestration, so that's the rate of change, but soil carbon stocks for the northwestern farm, the actual absolute amount also went down. So even with a beneficial impact of climate change on pasture, soil carbon stocks still went down. So that, you know, if you were enrolling in a soil carbon market, and that's a minimum of 25 years, the likelihood that the climate would change in 25 years is probably pretty high. So we looked at these adaptation mitigation bundles, and Brendan has talked about most of these before. Slightly different terminology, but mean the same thing. So we called it low-hanging fruit, Brendan called it adapt. That's just simple, immediate and reversible changes suggested by our regional reference group, and there were different regional reference groups in each environment, each location. We had this towards carbon neutral one, which was the low-hanging fruit one with additional farming systems changes stacked on top of it with the aim of reducing year-on-year emissions. We had this income diversification theme, which I think is synonymous with Brendan's grow and diversify, exactly the same aim. The aim there was to diversify income streams, so the same concept and slightly different details. Part of that was to diversify climatic exposure. So for the northwestern farm, we looked at purchasing another farm in the northeast, which is a different climate type to the northwest. And the transformational one. So that's similar to what Brendan and Nicole just presented. One of our regional reference group also asked the question, well, this towards carbon neutral one is all very well, but what does it actually cost to be carbon neutral? So what do we have to change and what does that actually cost? So I'll spend a little bit of time talking about that shortly. I'm not going to talk about the details. The individual components, basically a whole bunch of different farm systems changes, and they differed between farming systems. And I'm happy to go into the details if anyone's interested. I will say though that for the transformational one, that bottom dot point, we assumed a 20% or a 30% gain in genetic feed conversion efficiency of the animal. So by 2050, we assumed that feed conversion efficiency was 30% higher than what it is today. And we got that number from an expert scientist who works in genomic breeding. That's important because that's probably one of the big results that I'm about to talk about. What this graph shows is really just a trade-off between emissions reduction and the cost of a given mitigation option. So anything below the x-axis is a profit and anything above is a cost. So the width of those bars, the wider the bar, the greater mitigation. So similar to what Brendan showed, the biggest impact on greenhouse gas emissions of the farm was a reduction in enteric methane. We modelled a generic feed supplement that would reduce methane. We assumed it was Asparagopsis. We looked at two other options as well. So transformational feed conversion efficiency and planting 50 hectares of trees also had relatively high mitigation potential, 600 to 800 tonnes of CO2 equivalents. Feed conversion efficiency using biochar as a feed supplement, which we're trialling on farm, and renovating pastures with lucerne had come at the greatest profit. And that's because all those options had a productivity co-benefit, so they slightly improved productivity, so they basically come at the lowest cost. Planting trees, improving soil fertility, using a methane vaccine, which our regional reference group was quite interested in, even though it's not quite commercially available, but would be practical to use. All of those options come at a cost. We also looked at adoption. Most of those options that I've got on the screen, the regional reference group classed as relatively adoptable, except for transformational feed conversion efficiency, which obviously isn't available yet. And planting trees might be harder than you think with fertilisation and trying to plant at the right time of the year and ripping and keeping them alive and all that sort of thing. This is the similar chart to what I just showed, except I have productivity on the x-axis and farm gross margins on the y. And if you see that pink star there, I'm not sure whether you can see my mouse, but there's a pink star in the bottom left-hand corner. Anything above that pink star is a profit. And that pink star is actually where the baseline farm sits, and anything below that pink star is a loss. So if I just focus on Asparagopsis, which is that big circle down the bottom, feeding Asparagopsis to all weaned livestock, we didn't assume that we fed it to any unweaned livestock. It had the biggest effect on farm emissions of anything, but it also came at the biggest cost. Now, we didn't assume any productivity co-benefit because looking at the literature, it's all over the place. Some people say co-benefit, some people say nothing. So just to be conservative, we assume none. But really, this just highlights the trade-off between productivity, profitability, and emissions. So you've got the biggest effect on emissions, but you've also got the biggest cost. Buying an extra farm, which was synonymous to Brendan's grow and diversify, that had the biggest effect, or one of the biggest effects on productivity, because you've got more land area. Also had the biggest effect on emissions. And that's usually because of the tight coupling between emissions and productivity. What else did we show? I think that was about it that I wanted to say. The only other thing was wind turbines, which was part of that income diversification one. That increased farm gross margins and didn't have any impact on profit. We assumed that it didn't have any impact on emissions because the emissions would be owned by the wind turbine company. You could make an assumption that if it was counted as part of the farm business profile, then the emissions would be different. So this was really the main question. What does it cost to transition a farm to net zero? So there's a bit of detail in this slide that I'm about to show, so I'll just walk you through it. If you look at the baseline farm, there's about 4,000 tonnes of CO2 equivalents per year. You could offset all emissions by doing nothing and be net zero today if you purchased all of those emissions outright and make no changes. The problem with that was that it cost more than half of the farm's annual income. So if you look at that blue portion of the bar there, more than 319 grand to offset all farm emissions, which in a way is quite a good thing, because if it was one of the cheaper options, everyone would probably offset their farm emissions and make no changes, and the atmosphere would see no net reduction in emissions and no net global temperature change. Then we said, well, what happens if you just fed Asparagopsis or just fed an enteric methane inhibitor? Well, that cut farm emissions in about half, so it's reduced it by 1,800 tonne. So you'd still have to purchase another 172 grand worth of credits to get the farm to net zero. And then we said, well, what happens if you feed Asparagopsis and you plant 50 hectares of trees? That reduced emissions by another 800 tonnes. And then we said, well, what happens if you come along and you assume this transformational feed conversion efficiency? So we're feeding Asparagopsis, we're planting 50 hectares of trees, and we're assuming a more feed conversion efficiency genotype. That reduces your emissions by another 300 tonnes, but you're still above net zero. So you've made all these changes and you've still got gross emissions, so you'd have to purchase another 78 grand worth of credits to get to net zero. And finally, we said, well, we'll just scale up the amount of area of trees so that we are net zero, which comes back to the regional reference group question. We want a net zero combination. So we had 85 hectares of trees feeding Asparagopsis and a transformational feed conversion efficiency genotype, and that did get us to net zero. And your profit, your gross margin went from 550 to 638. So to answer the question, what does it cost? Well, it costs anything from more than half of your farm's gross margin per year to an income gain or a gain in gross margin associated with the productivity co-benefit. So basically multiple pathways to net zero, and the costs between them are very different. And there's other pathways you could get there. So instead of the tree transformational feed conversion efficiency option, you could have renovated the feed base with legumes or with lucerne, which is what we did here. Similar sort of result. We've gone from 550 up to 571. But obviously you have to feed Asparagopsis, you have to plant a large area of trees. And when you're talking about 85 hectares of trees, that's a big area of trees sort of thing. So just gives you an idea of the extent of changes that farmers would have to make to be net zero, which is pretty significant. But even when you've got a gain in profitability and a gain in productivity and a reduction in emissions, which would seem prospective, wider factors influenced adoption. So things like stewardship of the land and the people were classed as important by the regional reference group, as well as intergenerational sustainability. And climate change and carbon farming was perceived as complex. And so, you know, what is the truth and what's actually going to have an impact for my farm versus a generic farm sort of thing. Partnerships with learned people was seen as important. Dealing with risk and uncertainty associated with any given intervention was also perceived as important. And the transformational solutions, those that resulted in winning big and failing well, were perceived as transformational, and very much a need to balance risk. Risk was perceived as important, as well as the other things that I've talked about. There are more details. There's obviously a lot of assumptions behind that modelling, and they're both online. So that top one is published, and I think Franco is on the line, and the other one, costs of transitioning to net zero, is also online. That's under review. So just to sum up, we had modest beneficial impacts of climate change out to 2050 in Tasmania, at least at those two sites. Soil carbon sequestration will likely go down. We had trade-offs between productivity, profit and emissions, big differences between interventions. Really the ones that resulted in net zero were those that reduced enteric methane, because that's the farm's biggest emissions, sequestered carbon, for example, by planting trees. But the main one was if you had a productivity co-benefit, if you slightly improved livestock productivity by whatever reason, you actually had an improvement in profit. So that was the big one. We found a disincentive to offset and an incentive to inset. If you have a productivity co-benefit, your gross margins can go up and you could get to net zero in theory. Multiple pathways to net zero. I didn't actually show it, but planting trees had a bigger effect on farm emissions than soil carbon sequestration. And even when you've got productivity, profitability and emissions accounted for numerically, there's a wider social and institutional and psychological factors that influence adoption. So I'll stop there, Brendan, and hand over to the next person.
Thank you, Matt. Very interesting that the adaptation or the climate challenge is different, but some of the carbon neutral challenges are still there. So let's move now to Central Queensland, and I want to introduce Duc-Anh to you, and he's going to talk about the case study from up there.
Yeah, let me share my screen. Thank you, Brendan. Thing. Yeah, this is the one. Yep. Yeah, I hope that's everyone see it.
That's it. Thanks.
That's great. So good day, everyone. So this is Central Queensland case study, and I would like to acknowledge the great contribution from my college. And just to mention that we only consider 2030 climate here, and no option for carbon emission was studied. So the BIP enterprise we study located in Moras. So we see the climate pattern here, where we have summer dominates rainfall, and we see the land type variability on the property here. So the total land height 8,800 hectare, and we collect all the husbandry and reduction costs for economic analysis. And we should also note that we aim to develop a loose lease model of the poverty without a supplement and leukemia, trying to represent the average representative enterprise in the region. So the climate projection based on for 2030 were based on AR5 projection or CB 8.5, and we can see here they are very high confidence of warmer 2030 climates. However, there is a range in rainfall projection for all of the month, and we are not sure if it will be a drier or with high impact or a weather low impact future. So we use crust models for native pasture growth simulation and clam model for animal and host dynamic simulation. For adaptation option were models as suggested by the steering committee. So we look at the recent observed temperature and rainfall trend in Australia. We can see the warmer trend in temperature and a higher trend in annual rainfall at Mura, beef enterprise. Based on this observation, we selected the maximum consensus climate change scenario for 2030 climate impact assessment. So here are the results. So we can see trend of reduced pasture growth in summer and increased growth in winter. And it's interesting here that the time of initiating better growth in cold half of the year vary according to initial land condition. So with good land condition, the starting month in June-wise is earlier in May and April, respectively, for the moderate and full land condition. 2030 climate indicates similar or smaller variabilities of pasture growth throughout the year. The relative variability in pasture growth increase if the initial land condition get worse, as well as the 2030 climate's impacts on reducing the variability. But in overall, 2030 climate will reduce annual pasture production in all land conditions. So it is more interesting are the impacts of 2030 climate on livelihood gains of steer, and it's the steer the main cattle class for income of the beef enterprise. So it's interesting to see how small improvement in pasture growth in winter owing to warmer climate can increase livelihood gain in winter and also in September and October here by carry over effects. So the increased monthly livelihood gain are less significant with good land and more significant with full land condition. In annual basis, despite the reduction in annual pasture production, 2030 climates can achieve higher overall livelihood gain in all land conditions. This highlights the important contribution of better winter growth owing to warmer climate to specialized beef enterprise in central Queensland. So it should be noted that better pasture growth in winter were also found in other studies, for example, Brandon and Matt in grazing system of the South. However, winter is the main growing season and that's not a critical period for grazing enterprise in the South, but pretty different from Queensland, where summer is the main growing season and winter critical periods of fish shortage are typically associated with negative livelihood gain. So small improvement in winter pasture growth is just very important and demonstrated here for Central Queensland beef enterprise, but maybe for the whole beef production sector of Queensland. So this indicates the need for a large-scale study in Queensland. So it should be noted that the plots show increased livelihood gain per hectare, but we will show later the herd size needs to be reduced in 2030 climates, and thus the overall beef production will be reduced. In terms of adaptation, we found that 2030 climate can afford smaller sustainable herd size without deteriorating the land condition in long term. So reducing beef production and profitability per hectare land resource use. So among the 4 adaptation option models, improved pasture by legume crops is the best, allowing bigger enterprise development, more beef production, and better profitability. So conclusions. So future climate will be warmer and likely drier at the study region. So 2030 climate will reduce annual pasture growth, but in seasonal terms, warmer climate will increase pasture growth in winter and autumn, and thus weight gain in winter and spring, result in better annual weight gain. 2030 climate will increase drought sensitivity of the enterprise due to rainfall reduction with more dry days and longer dry spell. Better land conditions are more resilient to droughts. 2030 climate will reduce herd size, beef production, and annual income. Improved pastures is a promising adaptation option. And combining improved pasture and consumption rates and accounting for rainfall and necessity are the next step. Yeah, thank you everyone. So that's on my quick result for the Central Queensland case study. Thank you.
Thanks, Duc-Anh. Interesting to see the importance of the feed base and the improved pastures coming through in that case study as well as adaptation. If you can stop sharing there, I would now like to invite Paul Sanford. So Paul's from Western Australia, and so Paul Sanford and Kevin Foster are going to do a combination to tell us about their work in WA.
Thanks, Brendan. I'll just share my screen and get this into the presentation mode. Actually, it should be. Okay. Can everyone see that?
It's just still coming into, yes, perfect. Go ahead.
Okay. Thank you. This slide presents the team. With 7 people in the team. I'm just going to present the modelling results, which is the work of Meredith, myself and Emma. I did the pasture modelling, Emma did the crop, and Meredith the future climate. So I'll move on quickly. This is a lovely piece of work by Meredith where we're looking here at in-season rainfall. So that's the grain season rainfall in the current climate on the left and projected climate in 2050. On the right, Western Australia, the southwest of Western Australia has a Mediterranean environment, so that's winter dominant. And what this is for a relative concentration pathway of 4.5, which is what we are most likely expecting for southwest WA at this point in time. We also have modelled 8.5, but this is the less severe, so it's the more modest increase in temperature and drought. What you'll note is, if you look from left to right, is that grain season rainfall in that eastern wheat belt around Merredin is going to decline quite dramatically. So that red increases. The area in the red, which is 100 to 200 millimetres of rainfall inside the growing season. That's quite challenging. At the other end of the scale, you look at 900, the pink or the purple on the current rainfall in the corner there, and that actually disappears, and that's our actually where all of our forests are. So there's quite some big challenges both for native vegetation and also for agricultural production in southwest WA. If we have an 8.5 concentration pathway, which is if we emit more and don't do anything to stop emissions, this could be a lot more severe. In the modelling, for one thing to note about the 3 locations, they're sort of on a annual rainfall transect of 500 mil approximately in Kojonup of annual rainfall. Wagen is sort of 400, around 400, and Merredin is 300, just to give you a sort of overall picture. I modelled an enterprise which included which was the dual purpose merino, which is considered to be one of the most profitable enterprises in the southwest of WA. It's entirely confined to annual pastures at this stage. I will be modelling a lot of the perennials, etc., into the future, because our project is started after Nexus and we're about a year or a year and a bit behind them. So there's still a little bit of work in terms of the analyses to go. And that annual pasture was a legume-based grass and broadleaf, no crop stubbles in that. And I validated the model, which was grass grow using pastures from space. One thing I did do quite a lot of analyses of stocking rate at the 3 locations, and that was to determine what was the optimum sort of stocking rate, both in the current climate and into the future. We have looked at 2030, but 2030 is not different enough from our current climate, believe it or not, to really show any big differences. Obviously, it will be a little bit hotter and drier in 2030, but we're already in 2023 and we're already seeing climate change underway in southwest WA. 2050 gives us a much better picture of the contrast between current climate and the future. So on the y-axis, we've got stocking rate and ewes per hectare. The first 3 bars are cogonut, the high rainfall environment, and the first bar is current. And if you look at 2050 with an RCP of 4.5, which is most likely, we can actually, the model suggests that we can carry the same sorts of stocking rates in that environment also in the future. So that's excellent news. And even with a much higher emissions at 8.5, we see that cogonut would only experience a small decrease in stocking rate. In Wagen, the decrease in stocking rate for the 3 bars in the middle there, you'll see that even at 4.5, we see a decline in stocking rate. And in a sense, you can say these changes in stocking rate are in fact an adaptation. So we're adapting, but the only adaptation we're invoking in the model is stocking rate. And so at Wagen, that decline is more severe. But at Meriden, stocking rates currently are quite low, though we believe that there are a lot of growers, which is the ones on the 3 on the right. Meriden is around 1 ewe per hectare, but there are growers running higher stocking rates than that. But into the future, we could see a 50% or more reduction in stocking rate. Just to give you an indication of the change in pasture yield, the bars now have a line at the top and the bottom. That line is maximum minimum values for a 20-year run. The yields in cogonut are sort of around the 8 tonne, and they're unlikely to change into the future. That's the first 3 bars. And even the variation doesn't change dramatically, or doesn't change at all, really. Some of the minimums are a little bit lower. In Wagen, because we've changed the stocking rate, we've been able to preserve that, which is an adaptation, we've been able to preserve that pasture yield at around just over 6 tonne, and the variation is quite similar. But of course, it's a less profitable system because we've reduced the stocking rate to account for the hotter, drier climate in the future. Meriden, we're unable to, essentially, stocking rate is unable to provide sufficient adaptation unless we destock a farm to maintain pasture yield, and we see declines in pasture yield in that environment in the future. Variation's not increasing, but yes, that is actually where a lot of our concern lies. And just to give you an indication, stocking rate was determined by not feeding more than 30 kilograms of feed to a ewe per year, and also maintaining ground cover in autumn pre-breaker season, so we didn't erode soils. We've also looked at extreme climatic events. That's 2 drought years in a row, and just purely from the pasture perspective, and pastures recover after 4 years in the current climate after 2 drought years, and they also are able to recover likewise into the future, into the future climate. But of course, in the future, some of these systems are far less productive. But that's good news. Recovery isn't affected. This is my colleague's work looking at Emma. She's looked at crop yields. So we're looking at mixed farming systems here. And this is wheat and canola at cogonut in the high rainfall environment. And you do see, this is a box plot, 50% of the values fall within that box, and the line in the box is a median value, and the range is sort of described by the whiskers. And you do see that wheat yields in cogonut are expected to decline. There's no adaptation here. We're just purely growing a crop in the model. into the future, about in 2050 at both emission levels, and also for canola, there is a decline. Likewise, for Weigen, we see a decline, not a big, and for canola, actually for canola, you see much bigger variation in value. So the box grows, and there's a few outliers. So crops will be affected. This is for Meriden, which is the low rainfall environment, and the yield, just note on the y-axis, the yield values, they're smaller. So 3 tonne, or sort of a median value for wheat of just over 2 tonne, and they'll decline and again decline. So they mirror the pasture to some extent, but it appears that with stocking rate, that adaptation can overcome much of the decline in pasture, or sort of the effect of future climate on pasture in Duc-Anh and in Weigen. So what adaptations? We've yet to embark upon modelling adaptations. That's the next step. We're just about to commence that. In Duc-Anh and Weigen, sorry, pastures are likely to be able to adapt with current technology. So we already have trials underway in places like our research station at Duc-Anh, where we've been able to increase yield of forage crops. Perennials are increasing yield, changing the shape of the forage availability throughout the year. Grazing crops in winter, changes in grazing management. And we're very, very confident that these two environments, the high and medium rainfall environments in the wheat belt, will be able to adapt successfully with technologies that we have currently available. Adaptation in Meriden is going to be a big challenge and will require new innovation. So with pastures, a lot of the growers are already adopting low input, low risk systems. They're not prepared to take on high risk in that environment. It's based primarily on pasture legumes, but with high yielding annual grasses like ryegrasses. Deep rooted perennials are a potential option, shrubs and a rangeland system. It may be to the east of Meriden. Once you get outside the conventional agriculture, you move into a rangeland system, and that rangeland system may move west into that environment, so we may see more rangeland-like systems, contraction of conventional pastures to particular soil types and land management units which remain profitable. Some are sowing of annual legumes to really keep the legume in the system. They're currently losing legume content in their pastures. Soil mulching to conserve moisture, reduce stocking rate with a higher weaning rate, so less ewes, but producing more lambs per ewe, changing lambing time, turn them off earlier, all the sorts of things that you've been hearing from other speakers. Number of ewes joins dependent on season outlook, so you may not join all your ewes if the season outlook is poor. Changing the breeds, enterprise, confinement feeding, and the big one, another really big one, which I've put in red, stock drinking water and heat stress. In that environment, water for stock is going to become critical, and heat stress. So smart dams to reduce evaporation, shade, more watering points, etc. The adaptation for the crops, more drought and heat tolerant species in cultivars, time of planting, sowing earlier, change the proportion of cropping to pastures, so there'll be a different mix perhaps, more frost tolerant cereals. There's going to be more frost in that environment in the future as there's more cloudless nights in winter. Increase row spacing, change plant density, increase water and nutrient use efficiency. Thank you. I'll pass over to Kevin.
Question. So there's a question there, a couple of questions about carbon sequestration. So perhaps we'll start with those. One about the decreasing soil carbon sequestration rate that you mentioned, and if there's still an opportunity in future climates to increase carbon if you're coming from a low base, and also one in your accounting about whether you looked at baseline emissions. Did that include the sequestration?
It looks like I'm being saved by Kevin.
Well, do you want to just deal with them first while I
can do so. That on the one about soil carbon, we have another paper showing that it really depends on where you start, sort of thing. So the carbon level, soil carbon levels in the two case studies we assume was relatively high, and so therefore you're more likely to lose carbon with a warming climate rather than gain. This is soil carbon. We tried to ground truth them with regional measured data from peer-reviewed studies, but we didn't actually take soil cores on the properties. We didn't have the time or the resources to do that. But in general, a warming climate and warmer temperatures will increase soil respiration, and you lose more CO2 and the bugs respire more. And assuming it's a relatively high base at the start, soil carbon will go down. On the other hand, if you started from a degraded soil that didn't have much ground cover, your soil carbon could go up in future. It just depends on what ground cover does. So very context specific. Hope that answers the question, Brendan.
Okay, thanks, Matt. We found similar things in our work as well. So Kevin, let's cross back to you to talk about the case studies in Southwest WA.
Okay, thanks guys. So you can see my screen okay?
Yes, we've got it.
Perfect. Well, just first of all, thanks so much for the opportunity to present Brendan and Matt. And we've got very similar aims to the Nexus project within FutureShip as well, just looking at it from a Mediterranean point of view. So we're just about, as Paul said in the introduction, that we're about 12 months to 18 months behind Nexus. We're only just starting our case studies now. So this is our approach and to what we're going to do. And we're going to learn a little bit from what you're undertaking as well. So this is some work that Janet Conti will be undertaking. So we're aiming in WA to look at 6 producer case studies, 3 of those in the low rainfall region or the Eastern Wheatbelt near Merredin. And sort of Paul explained earlier on that that's our focus at the moment because we have the technology in pastures to deal with Wagen and Cogenut, but the real issue for us is the Eastern Wheatbelt. So Janet will be doing some in-depth face-to-face interviews and be covering things like what are they currently doing now with adaptations, be it around feed-based, sheep genetics, more water points or shade. What are those triggers for change and trying to put the climate change in the context of other drivers on the farm. Are they altering the enterprise mix? Are they changing rotations? Are they altering stocking rates? Are they conserving more feed? And are they using things like more within season forecasting? Where to get the information sources from? Is it from Duc-Anh or is it from consultants and their advice? And also, ask the producers themselves, what are their priorities for where they think the levy dollars should be spent. And as I said, Janet's doing this as part of her PhD and she's developing protocols. So the written case studies will be publicised with Duc-Anh and MLA web pages. And we'll also use what's GGA stands for Grower Group Alliance in WA, and that's our extension arm. And we'll be using those. And we'll also have 3 field days. And potentially we could do some video case studies with some of the producers as well in partnership with GGA. They're very keen to put this out there and extend it through their network. And then we're going to do some in-depth content analysis on the learning and extension for climate change adaptations. And then the outcomes from the FutureShip project for, if you like, a FutureShip 2 with recommendations for plan and investment by MLA and where the best areas to invest are. And we're also looking at, Paul introduced the 3 sites we're looking at the moment, which is Cogenut, Wagen and Merredin. But we're also looking at 3 other areas, which is sort of a little bit outside the project, but I'll explain why we're interested in those. So here's a map that you were seeing with Paul. And you can see there's our 3 areas, Cogenut, Wagen and Merredin. And this is what it might look like in 2050 in the RCP 4.5. And you can see how it's going to, certainly out here in the Eastern Wheatbelt, this is our major concern that our pasture feed base won't be able to adapt with our current tools. So for WA, annual legumes already play a critical role in our farming systems. We don't have a lot of perennials here. We do have some lucerne. Tadera is a new perennial legume that's been introduced recently. That's part of another project, Feed 365, but we don't have a lot of perennials in our system. This has just been released, this book, and it actually just released yesterday. That's an interesting species to put up on the front page. I wouldn't necessarily recommend using crimson clover in the Eastern Wheatbelt, but because that's sort of more of a medium to high rainfall option. But in WA, we've got about 9 million hectares of annuals across the wheatbelt. So you can see the importance that they already play in our systems already. And they'll become even more important in the face of climate change, increased end prices, GHG mitigation, and having to store more carbon. So this will be available soon. I'll put up a link and I'll send it around to Matt and Co, and you can have a look at it. So in WA, we've still got a pasture breeding program here, both public and private. So here's some new low to medium rainfall pasture options that have appeared in the last couple of years, literally. Sierra Max is a new yellow Cerridella, and it can be grown on acidic soils in 300 to 600 mm rainfall zones. And it can go much lower than that, actually. This is at southeast of Perth, near Newdigate. And this is the growing season rainfall. So it's about 220 millimetres a year, and this is what you're getting. So a really good option for those acidic soils, sandy soils, and for those low rainfall options. And here's the nodules. So look how much nitrogen that's laying down. Very impressive. And it's not only just this. This is a yellow Cerridella. There's also some new French Cerridellas, which is just a different subspecies of Ornithopus. And again, the beauty about these are they can be sown over large areas at a really minimum cost. The farmer can save his own seed and store it in silos, and it doesn't clash with the cropping programs. So here's the other one. This is the Frano Pink Cerridella that's just been released. And this is from Narrabeen. It's got a GSR about 260. In this particular year, he only got 220. Here's regenerating from a wheat crop. So the wheat crop was sown in 2021, and this is regeneration in 2022. And you can see, look how dense that is. And here's some sheep grazing the same crop. And here what it looks like in spring. So there's about 30,000 hectares of Frano sown across WA in that low to medium rainfall zone in 2022. And we were talking before about other aerial legumes. The spice rule has been sown in the eastern states of about 20,000 hectares as well, mainly around New South Wales. And here's Frano again. So this is what farmers can do. They can sow the seed and have like a nursery area. They can grow it, and then they can harvest their own seed. Here's a farmer here using a traditional cereal harvester to harvest his Frano pasture. Now he can store that for next year. That's potentially feed. And here he is where he's actually left some of this standing crop here as a source of feed for summer. And the other case studies I was talking about in introduction were, here's our three main areas, Merredin, Wagerin and Kojonup. But as I said, we're really concerned about our options for the Merredin region. So here's Beacon. Now Beacon's sort of on the edge of the pastoral area. It's almost on the edge of the rangeland area. And they've got a very interesting system out there that we're looking at. We're also looking at a Cullen. We're about to produce a paper. We've actually just submitted a paper about Cullen site and their adaptation methods. And also Mount Barker. Now this is a sort of more of a high rainfall zone, but even down here, the work that Meredith has done has shown that they will not get away without being affected by climate change, and quite dramatically actually. So the producer here is actually going to be part of a new study, and she's going to be in the upcoming MLA feedback article. I think it's in the spring edition. And here's the Cullen site, and this is a paper we just submitted just now, and a whole new range of questions for researchers. And this is where it sits, so in the medium rainfall zone in Cullen, in the southeast. That's its area down there, and that's been a very interesting exercise to undertake, with the full help of the producer. And here's a bit more about the Cullen site. It's 60-40, so 60 pasture, 40 crops. He's got nearly 5,500 hectares, and he's transitioning from using lots of nitrogen to basically using pastures. He uses nutritional packages, which that's under a bit of IP. We don't know exactly what he does. And what we're doing through that paper is we're examining the economics, the carbon emissions, and the climate resilience on that farm, with the hope to be able to extend that out to other areas. And we're doing some evaluation modelling through SUD. And at the moment now, from what we can understand in our analysis, by the standards, industry standards, his GHG emissions are quite low, and his soil organic carbon is very high for the for farms and similar systems. This is what Beacon looks like. As I said, almost on the edge of our rangeland. You can see here this is just perennial and annual grasses, and some of these are yet to be identified. And we think, as Paul said, this is an area that might start moving more west. So this is a sort of environment that we might be facing in 2050, closer towards Perth. And this is in the central wheat belt. They've got about 25,000 hectares. The beauty about this is it's really low input and it's a really low risk system. Current grazing system is operating as a pastoral rangeland system. The flock size varies between about 3,500 to 7,000, and it's got a very low stocking rate. And their focus is really on soil health as a main driver of productivity and profit. And, you know, in this system here, there's actually no legume present. So if you could put something like a yellow Cerodella in here and have it drive the system, the productivity lifts you'll get here and the lifts in cycle rate would be enormous. At the moment, they haven't done that, but I think there's real opportunity to improve this system here just by simply introducing the legume. And that's it. Thank you very much for that.
Thank you, Kevin. And thank you to all the presenters. I might invite you all to put your cameras on now. So I won't spend too much time wrapping up, but I think a couple of points come out about the challenges of adaptation. You know, we've seen some regional differences, but we've also seen some commonalities across the sort of adaptations that people are thinking about and how to address this challenge. The carbon neutral story, certainly a challenging one with current technologies, and a lot of our producers are raising questions about, well, how can we use them? What are the advantages? Are there pasture-based solutions that we can use that, or how can we implement additives into our pasture-based production systems? A lot of questions about feed base, how to maximise feed base in this warmer and hotter climate. So there was a whole lot of research and development questions which have been identified through the modelling and also through consultation with our reference groups. So I might just spend a couple of minutes going through the questions that are there before we finish up. So a couple of questions pertaining to trees. So we've simulated trees in a couple of different ways. Sometimes they were environmental plantings on the farm, which are going to be there for a long period of time. Other times there's an agroforestry, or no, a forestry block purchased, more like a woodlot. So depending on the location and the suitability for growing trees, we've done that in both ways. There's a question here for you, Duc-Anh, about the breeds of cattle. Did you assume breeds or breeds? And in a future climate where ticks may not be controlled in taurine breeds, would that change some of the outcomes?
Yeah, definitely. The breed that we use in our case study were the indicas, sport indicas, and we did impose the tick vaccine there. But in terms of Taurus breeds, we are not sure, and I think we can still impose the tick vaccine there, but it depends on the modeling capability of crop and livestock enterprise model, the claim model at the moment, because what I know is that only the genetic parameter of the both indicator is available at the moment, not the Taurus one. So, I think CSIRO are working on improve the claim model very quickly. So hopefully we can have that soon, and we can see, that interesting question and effect there. So how impact on the production outcome here? Yep. Thank you.
Thank you. Matt, a question for you about the improvements in feed conversion efficiency that you assumed.
Yep.
So I think it's a really interesting, in terms of both adaptation and potential for mitigation, a really interesting area. So can you talk a little bit about that, about if that's specific to breeds or any potential trade-offs with selecting for feed conversion efficiency?
Yeah, so feed conversion efficiency, just to step back one, is the amount of live weight gain per unit feed consumed. So if I ate 1 kilo and I put on 1 kilo of mass, something that was more feed conversion efficient would be eating 1 kilo and putting on 1.5 kilo, for example. So we went to animal breeders, livestock breeders, who actively work in genetic breeding of sheep and beef. And they suggested to us that a stretch target might be a 10% improvement in feed conversion efficiency per decade. So out to 2050, we assumed a 30% increase in feed conversion efficiency relative to what we are today. And we put those parameters into the model. So basically the animals, ideally the animals would put on more live weight per unit pasture feed consumed. And we showed that because that had a productivity co-benefit, that was actually one of the most prospective options. And it's obviously a genetic thing. You do tend to get sort of slight trade-offs in the model though. Feed conversion efficiency goes up and we saw feed consumption go down a bit. So they didn't put on as much live weight as what we'd expected. So you do get some compensation. Feed conversion efficiency also influences methane emissions as well. So they're all sort of interlinked, and that's dependent on a genetically improved genotype under future, but the animal scientists suggest that that's realistic. It's generically applicable to beef or sheep or anything that you assume, I think. So I think the person that we spoke to was saying it was beef and sheep. So
okay, thanks, Matt. One last question there for now was about the methods for incorporating and valuing carbon credits in future environmental markets, such as the nature repair bill. So I guess the approach that we'd taken in our work was more to look at insetting rather than trying to sell carbon credits from the farm. So looking at it in terms of market access, producing low carbon products. So we did look at some scenarios where a carbon tax or some other method of payment might be required, and looked at our carbon neutral farm systems. And certainly if there's a carbon tax or a requirement to buy carbon credits, then that does lift the carbon neutral farm up a little bit compared to the other adapt and grow farms, but it still was sitting a little bit less profitable than the other farm businesses. So yeah, mainly we focused on insetting, but yeah, there may be other opportunities as well. Did you want to comment on that, Matt?
Yeah, we had slight differences between your project and ours. I think in those charts that I showed from memory, don't quote me on this, but I think we assumed a future carbon price of $100 per tonne of CO2 because we assumed a future price. It's less than that now, but we assumed that that's what might it be in future. The question asked about environmental markets, the nature repair market bill, we didn't include that. So it was just a high level, simple economic analysis in what I showed there. And you could do all sorts of stochastic modelling with the economic stuff as well, which would be a good question, but we didn't, that was out of scope for what we did.
Yep. Okay, thanks, Matt. Look, I think we'll call it to a conclusion there. We've answered the questions in the chat box. Obviously, there's a lot of detail behind the work that goes on in a project. We've tried to present a snapshot. If there's any questions, feel free to email any one of the presenters here or get in contact. I'm sure we'll be pleased to respond. Thanks everyone for attending the webinar today and hanging in there till the end. So thanks everyone. Thanks to the presenters and thanks everyone for attending, and enjoy the rest of your day.
Thanks, Brendan. See you all.
Thanks,
See you
Brendan.
later.
Thanks
Yeah,
all.
bye. See you all.